predicting the next word in a sequence of words, and also predicting classification, I think classification of sentiment. So if we worked on, say, using a hierarchical LSTM for classification of given text, say, for example, a review, IMDb review, to classify whether it's a positive or negative review. So what we were doing is basically, first we laid the foundations of what was neural networks and deep learning. And then we looked at specific applications, particularly related to sequences or one-dimensional sequences of data, particularly like text. I mean, it need not only be text, it could also be, say, the same thing like LSTMs and GRUs could be applied, say, in predicting any kind of time series. A time series, so like, for example, weather data, so one-dimensional data. So there we saw specifically the shape of a neural network is geared towards the type of problem that you're trying to attack. So I think last month we went back to, because some people were asking, okay, let us go back to the basics and go through them again. So last month we went back to introduction to TensorFlow and Keras, and the use of the TensorFlow in R, basically how you handle tensors, doing multiplication, tensor analysis, as well as what you do in simple application like TensorFlow for linear regression or TensorFlow for classification. Now we are going to look at a specific type of neural network called convolutional neural network, and this is kind of network whose architecture is designed for image analysis. So the standard neural network, let's go back to what is a standard neural network? Based on the architecture of neurons in the human brain or any animal brain, this was the inspiration for the development of this machine learning model, where you try to imitate. So, like for example, the eye sees something. Certain electrical signals are sent to the brain, and the brain is able to process that and determine, okay, am I looking at a cat or a dog or a tree or whatever I'm looking at? So, and how does the brain work? Well, there is of course we still don't know exactly. What we have is a certain simplified model called the perceptron. So we have biological neurons, which consist of certain cells which are connected to each other. They send signals to each other, and that entire process results in the the computational effort required for the neurological processes in the brain. Now, our aim is to try to model that as best as we can. Of course, we still are have a long way to go to actually understand the full complexity of the brain. But what we are doing is basically abstracting out from that the basic idea, and then using that in, say, teaching us, say, a machine, a computer, to imitate that in some simple, basic way. So abstract out the network of neurons as a collection layer, and that's what we call as a perceptron. So this is a kind of a toy model of a neuron that we are building. So the simplest neural network consists of, well, you have a set of inputs. Generally, you will have a set of inputs. So in any machine learning model, you will be given inputs and outputs, and your job is to take, say, inputs or what are called the predictors, and predict out the output. The output can be some kind of either a classification, or even you might want to be you might be interested in, say, detecting where in an image a certain item of interest is located, say, or you may be interested, like what we are looking at, as predicting the next word in a sequence of words. So the output can be categorical, it can be numeric, and in the input you will have basically whatever data is given to us. So we will generally have multiple inputs. If they are categorical, we will convert them to numeric by some kind of dummy variable creation and so on. But in the input, you will have, suppose here you have in this neuron, you have 3 inputs. So 3 numeric values are sent in. Each one is then sent to what is called a perceptron. The perceptron does a simple mathematical calculation. It just takes the bunch of inputs and does a linear combination on them. Say these three inputs are taken, it does a linear combination by using certain weights and biases. Weights and biases simply means what we call slope and intercept. This is just a linear combination, and then normalizes that result. So the output is then sent to something called an activation function, a function which will then add some non-linearity to the model. Otherwise, you will just have one linear model on top of another. So in order to add some non-linearity, you'll send it to an activation function. And then this process is gone. Now this layer of values, so some values will be generated here. This layer of values is then sent onto the next layer and so on. And finally, in the output layer, you will have, well, the outputs that you are interested in. So in this case, there are 9 neurons, the 3 input layer, 4 plus 2, 3 plus 4 plus 2. And in the output layer, you will be getting out the data that you are interested in. And the way in which then the goal of the training of this neural network is to find out the correct weights and biases at each level. So in this case, you have what is called one hidden layer. And this is also known as what is called a dense neural network. The reason it's called dense is because you have an input layer, you have a hidden layer, you have an output layer, you have multiple layers, and the connection between each layer and every other layer is dense, in the sense that every single perceptron in one layer is connected to every other perceptron in the next layer. Each one of these three is connected to each one of these four. Each one of these four is connected to each one of the two. So this is called a densely connected neural network, and that is, you can think of that as the most general form of a neural network. And of course, the goal of the machine learning is to try to find the correct weights and biases so that you get the outputs that you want. So the outputs then have to be trained against certain labels that are known. We expect the outputs to be such and such. And then we find a loss function, some error function, and minimize them with respect to the weights and biases in order to find the weights and biases that will give you a correct output. And then you say the neural network has been trained. Now, this is the general structure of a neural network. Now, based on this, as we were looking, based on the specific type of problem, if you have some kind of sequence, like sequence of words, or sequence of time series, like, say, stock exchange data, or say, sequence of, say, weather readings from day to day, that is weather data. If we have a sequence, then there will be certain structures of neural networks that will be geared towards handling that kind of data. Similarly, for images, what we will be using is what is called a convolutional neural network. First of all, we need to understand, well, how are images represented in a computer? Well, an image is generally represented by an array of numbers. So suppose you take an image like this. From the top left-hand corner to the bottom right-hand corner, every single pixel, so the image consists of an array of numbers, each one is called a pixel. Now, at each point on the image, the pixel will simply tell you, well, what is the color at that point. And so if you can just say, specify the color along every single point in a rectangular array, then you have specified the image, right? So what you will be feeding in to your input layer will be something like a set of pixels, a set of colors ultimately. And now the colors will then have to be coded in numeric form. So the color generally is coded as well. How much of red is there? How much of green is there? How much of blue is there? And there will be certain shades, like going from 0 to 255. 0 means nothing, and 255 means maximum along that color. So if you have a code saying 255, 0, 0, that means you have maximum red, no green, and no blue. So you have for an image, for a colored image, you will need to have 3, specifying how much of red, green, and blue there is in every pixel. So you have a 3-dimensional stacked view of RGB. You can write it in your hexagonal code or decimal code, whatever that doesn't matter. But for each color, you have this range of numbers, 0 to 255 generally. So you will either be working with colored images, or you'll be working with what are called grayscale images, where you don't just have what is RG and B, you just have a scale between white to black. 0 means white, 255 means black. In which case, you will not have these 3 channels. So at each pixel, you'll just have one number indicating the shade of gray it is between 0 to 255. So the thing is this, that you could take an image and then pass it on, from input layer to hidden layer to output layer. You just have to take, say, an image. So in this case, you have 3 input perceptrons. Well, for an image with, say, 411 by 528 pixels, you just have to take each one of them, put them as one value in the input layer, and then pass them on to the hidden layer and so on. The problem comes because there are too many values, and the 411 into 528 input values, and then each one, if you want to work with this kind of neural network architecture where each neuron is connected to every other neuron in the next layer, then you'll have too many weights and biases, and that makes things difficult. The question is, well, can you extract out, because we are dealing with an image, and in an image, what really matters is, if you think about it, to identify, suppose you want to identify the image, what really matters is the boundaries, right? So can you, extract out information about just the boundaries, or only certain features of the image are what really matters? So it's not that any random collection of pixels would form a meaningful image, right? We will have essentially continuous extended objects which are suddenly ending in edges, and it's the shape of the edges which will really specify for you what the image is. So can we extract that out and use that information to simplify the neural network, so that you don't have a dense neural network, but you want to actually have a network that will pick out the relevant features only, the features that you are interested in. And that is what is done by convolution. So here, instead of using, say, arbitrary weights and biases, you use a set of weights and biases called a filter. And then that is just passed along the entire sequence of, it's just passed through the entire array of pixels. And so you say, suppose you take this filter 1, 0, 1, 0, 1, 0, 1, 0, 1, and you then put it as a kind of, put it around here in this blue region. Then you just do a product sum, multiply it with the pixel values and add, you get 4. And then you just slide the kernel and across the entire region of the image. And what you get is then, it is going to determine, well, whether this some particular feature which looks like this is sitting somewhere in the image or not. Because if for example, you just have a bunch of zeros and ones here, this will be maximum when this particular pattern, this kernel, matches exactly on the image. Maybe, so just a minute. Okay, this is done in mathematics, we will skip that. But basically, suppose you have, say, an image of a mouse. What you will, suppose you have a kernel like this, and I want to identify whether this particular section exists in this image or not. So this particular kernel is then converted to this kind of matrix, and this is then moved along the image. And at each stage, as you move it, you just keep doing a product sum of this matrix with the actual the entire array of pixels which represent this. So you will find that when this particular black line, which is represented by these high values 30, 30, 30, 30, matches this particular location on the image, they will all add up. I mean, they will all multiply to a large set of values. So in this, say, you just take a zoom in of this particular region of the image. Sorry. If there is a product, I mean, if basically this shape matches exactly with that shape in the image, then you will get a sudden spike. So you will be able to use this kernel to identify whether this particular feature, this particular part exists in that image or not. If it exists, you will see a spike there. Then you'll see a huge value. Basically, these positive numbers will be multiplied. Otherwise, you won't see, because otherwise these positive numbers will be kind of overlapping with some zeros sitting there. So you won't be, and so the product of 0 and any number will be 0. So you won't see that kind of spike unless this shape of the kernel matches some feature in the image. So you just multiply and sum and you get a huge number. So as you move the kernel along the image, if there is a spike somewhere, that means that kernel or the feature that that kernel is searching for is sitting in that image. So now, of course, suppose you want to do some analysis, say suppose you're given a set of images and you want to classify them into whether they are cars or planes or boats or trains or something. You will need multiple kernels because it's not just that a car has one feature. Car will have multiple features, right? And we have to have multiple kernels. So there will be actually multiple layers of this process going on. So not only will you be doing, so this is an entire set of, we'll just look at the overall process first. So suppose you have directly from the image, you have an input here. You will be taking multiple kernels and creating what are called feature maps, which are simply the outputs of this convolution process. The convolution process is defined as just taking this kernel, sliding it along the image, at each state doing a product sum. Just multiply 1:1 and then add. So this you do for not just one kernel but for multiple kernels. Now so now we have done that, and suppose suppose you have a trained neural network. The kernels will be designed in such a way as to extract the features that will indicate whether or not, say, the image is a car. Suppose I want to detect whether the image is a car. The kernels will be designed, they will have to be designed. We still have not done that. The kernels themselves will have to come out of the training of the model. But they will have to be designed in such a way that they will extract out the features. And then, so you do that product sum, and this is what the star means. You take each of the kernels, do that product sum on a previous layer. Now we will look at, okay, how many layers there are. But initially you will have either an image which is a color image, in which case you will have 3 layers like this. You will have basically 3 layers. Each one is an array of pixels, right, for red, green, and blue. Or if you have, say, a grayscale image, you will just have 1. Now you do that for, and of course, add a bias as well, and then apply an activation function, which will simply normalize it so that the output doesn't keep on increasing from from across every layer. Otherwise, you just keep on doing product sums and adding. You need to find some way of normalizing it. So for that, we will use an activation function. You can use tan hyperbolic, sometimes other activation functions like ReLU and other activation functions are used. Also, suppose, okay, we have, at this stage, suppose, okay, we have identified like this particular, this particular feature is there in the image, and we get a spike. But we want to preserve that information while at the same time reducing the number of pixels, because ultimately you want to take out these thousands of pixels and get out just a few numbers indicating the probability of, say, suppose you want to do classification, you want to indicate the probability of the image being a car or a plane or a boat or a train. So you want to extract out a few numbers from a large set of numbers. So what you need to is, so now that you have identified that a particular feature exists, and that exists by a peak in that, once you have done the convolution, you get a peak. You should also be able to keep that information while also reducing the number of pixels from one layer to the next, until you finally are able to bring it to a small set of numbers, which can then be interpreted in the way that you want. So what you do here is called MaxPooling. That is to say, you take, say, 2x2 sections of the convolved image and then keep the maximum in every 2x2 section. So this pink section is there. What is the maximum of that? 6. Then look at this green section is there. Maximum of that is 8. So now the blue section, maximum of that is 3. And here also yellow section, maximum is 3, blue is maximum is 4. So you just keep the maximum values, and what it does is, well, it has reduced the number of pixels, but if there is a peak anywhere, that peak information will be there. So that the fact that there was a peak somewhere, that information will still be there. But you have brought down the number of pixels, and this is the process you keep doing over and over again. So you do a convolution, then reduce the number of pixels by MaxPooling, then another layer of convolutions, and then bring it down by MaxPooling until you have brought it down to a small enough number. Then later you might want to have, say, a standard fully connected or dense. When I say, okay, fully connected is the same as dense, fully connected neural network. And then finally, suppose you want to simply do at the end, if you want to just do a binary classification, you will just have one output at the end, which will be interpreted as the probability of one or the other. If you want to do multi-class classification, well, at the last stage, you will need however many classes there are. You will need that many output neurons. So this is the entire process, and in that process, we have weights and biases at each stage, set of weights and biases, and that will essentially determine what features the kernels are searching for. Just another version of it. Okay, so just to to understand what is going on here. So suppose you start with a 64 by 64 image, and you use 5 by 5 kernels. Now you just keep sliding this 5 by 5 along the 64 by 64 image. You will get a 60 by 60 feature map at the end of it, because this particular kernel cannot go out of this bound. If it just moves from one end to the other, it will move from one end to the other in 60 steps. It'll just hit the boundary after 60 steps. So you get 60 by 60. And then suppose I want to use 10 kernels to extract out 10 different features. I'll be having 10 of these feature maps after the one layer. And then now using MaxPool subsampling with 2 by 2. Now you're doing 2 by 2 fields, so the 60 by 60 will go into 30 by 30. Just like we saw that 4 by 4 went into 2 by 2. Right? So this is one layer. Then the same story is now repeated with another set of kernels. Now we use another set of 5 by 5 kernels here. Now this of course the size of the kernels itself is a hyperparameter. It's a parameter that we have to select. If you want, you have to tweak that and modify that. So again, 30 by 30, and remains 10 here. Now you can also take it now to the next level. Remember, okay, just doing MaxPool subsampling will not change the number of feature maps. We had 10 feature maps. Each one of them has simply been reduced in the number of pixels. So 60 by 60 has gone to 30 by 30. Then again, you use a 5 by 5 kernel to do convolution. And suppose we want to say change this 10 to 16. From each of these 10, we'll now pull out 16. 16 feature maps at this level. So now you have 26 by 26 by 16. Again, you do MaxPool subsampling. 26 goes to 13. 26 by 26 becomes 13 by 13. Then you just flatten it out. That is, now take out the image, and the image will no longer considered as an array. You just flatten it out into a one-dimensional array. Then say keep doing fully connected layers after that. Now you just deal with it as a one-dimensional array of neurons, and then the output from here you keep on doing fully connected layers until you get to the final output. So okay, the training of the model is done by the standard way in which any neural network model is trained. You have to find out a loss function, determine a loss function so that it is minimized when the model is doing what you want it to do. That is, it is giving the predictions that are the correct predictions. So some kind of function like this, you sum over all the samples, prediction minus actual, either square it. Well, this is just a sum of square of the errors. Now, if you want to, okay, this is the loss function, and this will obviously be a function of all the weights. So all the essentially all the features here, the entire set of numbers that determine each one of the kernels, as well as the biases at each stage of the process. So there will be thousands, tens of thousands, maybe even millions of parameters. So those will be the parameters with which with respect to which the loss function has to be minimized. Now, okay, how will we do this now? Because it is not an easy problem, because you have to change so many parameters. Well, the way in which this is done is by gradient descent. It is, you calculate the gradient of the loss function with respect to all the weights and biases, and then move. You keep doing a kind of iterative procedure, whereas you by essentially moving the weights and biases, changing them by one step at a time, in such a way that it goes in the opposite direction of the gradient. Something that you should have had. Anyways, now the process of gradient descent is much easier done when you work with a smaller set of samples. So generally what is done is you take a subsample of images, and then apply the gradient descent technique on one round, and then take another subsample and then apply the gradient descent for the next round, and so on. So this is an iterative process where weights and biases are constantly being changed. So take a random subsample of the data, find the gradient, optimize the weights and biases, update them, and then take another random subset, find the gradient of the loss function, and update the weights and biases, and so on. Okay, so this is not, we will not actually be looking at handwritten digits. We have seen this in one other class before, but let me show you for what is called the CIFAR data. So this is a data set which is just, you can see online what are the and some examples of images, CIFAR 10 data set. So it consists of multiple classes like airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. There are 10 different classes, and you have a set of images which can they are all of the same size, 28 by 28 images, and they have, an airplane taken. We have photographs taken in various locations, various angles, and so on. But the purpose is to now, given an image, it should classify correctly which of these classes it is. So it's a 10 class classification problem. Given the image, the job of the neural network is to classify the into which class it belongs. So this data set is sitting, actually this is in already it's one of the demo data sets in Keras, so I'll just load it directly from here. In fact, I've already loaded it. There are 60,000 images in the training data. If you look at the training data set, there are 60,000 images. Each one is a 28 by 28, and right now it is in the grayscale form. So in other words, there is no other dimension. There is no dimension of color. If it was a colored image, this has actually been converted to a grayscale. So those colored images have been converted to grayscale images, and there are 60,000 in the training data. So this is the training predictors consists of 60,000 images, each one being a 28 by 28. So this is a three-dimensional array of pixels. As I said, the values go from 0 to 255. It makes sense to divide by 255, in which case it goes from 0 to 1. Keep that as the training data. And that will be 60,000 by 28 by 28 by 1. In this case, we are using grayscale images. Otherwise it will be 3. There will be 3 colors. Similarly, for the test data, there are 10,000 of them, the same structure. Now, the outcome is one of those 10 classes, right? So look at mnist $train $x or $y. Head of that. So it will be basically some numbers between 0 to 9 indicating one of the 10 classes. This is, this is standard. It's arranged in alphabetical order. This will be 0, 1, 2, 3, all the way up to 9. So our goal will be to predict, well, what is the probability of it being an airplane, or what is the probability of it being a ship, and so on. We can take the X data and view it also. We'll not be able to get, say, view of $train $x of 1, comma. By just looking at this, I can say something. What it is, probably not. But so this is basically one grayscale image. You have a bunch of whites. 0 stands for white, and 253, 255 is pure black. So this is the first image, and so on. So similarly, you have for training and testing. Now, what you want to do is to extract out from the label the probability. So if the label is 5, it simply means the probability of class 5 is 1, and the probability of all the classes is 0. So the way you do that is to convert it to categorical. That is, say, you take these 9 classes or these 10 classes and write them in terms of the probability. So probability of 0, probability of 1, probability of 2, all the way up to probability of 9. So that's what you do in converting it to categorical. So if you look at Y train, okay, so this is 0. So V1 is essentially class 0, V10 is class 9, and this one is class 5. So under class 5, you say 1. So this is the target we want to predict. So whatever be the neural network, it has to finally give out a set of numbers, which right now V6 is class 5. The probability is 1. We know for a fact the output is that the probability is 1 for class 5 and 0 for all others. So the output class is known. We need a neural network that will actually predict this. It will predict 0 for everything else and 1 under class 5, and so on. So I'm going to use Keras. Keras is a high-level library. We have used it already, I think, for RNN. Keras, it can be used on TensorFlow or on some other tensor manipulation platform. So right now I'm going to use Theano. So it has been, it's a kind of high-end library that uses as a backend some tensor manipulation libraries such as either TensorFlow or Theano or CNTK. These are the 3. So I'm going to use Theano in the backend. And so there are functions in Keras which allow you to build the model step by step. So start with model as defined it as a sequential model, and then keep building on it layer by layer. So initially you start with a 2-dimensional convolution. So this is the process of going around to convolutions and then MaxPooling, convolution and MaxPooling, and so on. So the layer conv 2D does actually begin with convolution and goes down to it also does MaxPooling, and on top of that you add an activation. This is done step by step. So here you start with conv 2D, you give a kernel size, you specify the input shape. This is actually the input shape is base 28 by 28. So 28. Then you do an activation function, apply it to, and then send it to another convolution layer, say. Then again do an activation function at each stage. So now we initially started with one channel, right? We started with just red, instead of red, green, blue, we started with the grayscale channel. Bring it to 32. Then take it to another convolution layer. Then you do max pooling. Use a pool size of 2 by 2. Now I'm also adding what is called a layer dropout. Now this is useful because what happens is that there can be overfitting. See, in any kind of complex model where there are too many parameters, there can be overfitting. That is to say, it fits very well with the training data, but that is because it is fitting some kind of features that just happen to be in the training data, but they are not actually representative of the population as a whole. So this happens for any kind of complicated nonlinear model. And the way in which you overcome that is, in here you can add what is called a dropout. That is to say, I drop out about 25% of the connections, or 25% of the weights connecting, say, one layer to the next. I drop them out randomly. And so every time the model is trained, a different set of connections are dropped out. So that the model is not overly dependent on just one set of connections. So this adds a bit of robustness to the model. You drop out some percentage of connections. Every time you run, you do a random dropout of some weights are essentially set to 0, and about 25% of them are randomly set to 0 at every iteration. Now another set of layers, another convolution set of layers, max pooling. Now you bring it up to 64 different features and keep doing that. Then you flatten it. That is, you no longer treat them as images, you just flatten them into just one sequence of perceptrons. Then send them to another set of, another layer of dense connection. What I call dense connections is connection from one layer to the next is from every neuron to every other neuron. And then finally bring it down. We ultimately have to bring it down to just 10 different numbers, right? Which then have to be interpreted as probabilities. So bring it down to 10. Now we have used all the way down what is called a ReLU activation function, what is called rectified linear unit. So here, what is done here is that all the negative numbers are cut off and sent to 0, and all the positive numbers are kept the same in ReLU. And you're applying this after every convolution, you send it to ReLU activation. At the end, we add what is called a softmax activation function. Now this, what it does is, because the output needs to be interpreted as the probability of 1 of 10 classes. Well, a probability has to have two characteristics. One is they all have to be positive, and also a probability has to be positive. And the sum of all the probability of all the classes has to be 1. And this softmax essentially does that. It converts the output of this layer dense is then converted to strictly positive by taking exponential. And then it normalizes with respect to those 10. So that the sum of all the probabilities is sent to 1. So the model is now constructed. Now use an optimizer. This is we talked about gradient descent optimizer. There are certain other variations on gradient descent which allow for some more. They are a bit more sophisticated in the sense they allow for, say, changes in multiple directions on weights and biases. Different kind of so you see some weights and biases you have to change a lot because they'll be way off the optimum. Some weights and biases you have to change less. So depending upon how much you have to change, you have to take steps in various directions, or rather along various weights and biases. The steps you need to take will be different. So there are certain algorithms which have been developed to do that more efficiently. One is called RMS-prob. That is what we are using as optimizer. You can then calculate the accuracy at each stage. Now there is another feature that is unique to dealing with image data. See, in image data, what you one of the difficulties in neural networks is that you need to have a lot of data. You need to have a lot of training data in order to get a really good neural network. And what happens is that the image data that you have now is, it may not be enough. Even though 60,000 images that we have for the training data may not be enough. So you can augment it by doing some kind of changes. See, an airplane is an airplane, whether it is, and that will be the same even if you flip the image from left to right. You can say change the image by, say, rotating a little bit. We want to allow for as much variation as possible in the training data, so that all the possible options can be, the model can be trained on various possible options. So we want to have, they want to be able to say zoom in and zoom out a little bit, so that cars of all shapes and sizes, so that cars, whether the image has been zoomed in or not, it should be trained to detect it. So we want to say zoom in, zoom out. So there are some variations we want to keep adding on the images and augment the amount of data. So that is called data augmentation or image augmentation. And Keras already has a function which does that, where you has a function called image data generator. And well, there are some things like feature-wise center. Basically, you want to normalize the range of so centering and normalization of the range of values in the pixel. For example, you want to say, suppose the pixel values we had seen goes from 0 to 255. You can normalize that to 0 to 1. Say you can either, or you can normalize it to -1 to 1. That is, say you want to center and normalize the pixel values, or you allow for a little bit of rotation. So allow for, say, 20-degree rotation on the image. So as you keep sending in batches of training data to the model, you keep rotating the image randomly all the way up to 20 degrees. You allow for a little bit of width shift. That is, you shift, you kind of zoom in and zoom out along the width, or zoom in and zoom out along the height by a certain fraction, or something between 0 to 0.2. This is a range that is allowed. It's not exactly 0.2. You allow for a maximum of 0.2, but you allow a range from 0 to 0.2. And then every time a batch of images is sent in to the training data or to the model, you allow this kind of data change is done, and this allows you to augment the images. So initially you had 60,000 images. You can just keep on generating additional images, and that actually increases the variation in the training data. So that allows you to kind of train for different possibilities that, in fact, certain. So for example, if you have trained, say, for an aircraft facing to the left, you want to be able to detect an aircraft facing to the right as well, right? So you allow for horizontal flip and then send that also to the training. So anyway, the process will take some time. We have already run some of it. Right now, the accuracy stands at, for the training and validation, we have accuracy and validation accuracy, loss and value. So what is the loss function we are using here? We are using multi-class, or what is called categorical cross entropy. This is a way to essentially, this is a loss function. This is not exactly the same as the mean square error. This is a different kind of loss function. And that obviously is, we keep going down. And here we are plotting epochs. And when I say epoch, I'm talking about an entire run through through all the 60,000 training images. So this 60,000 will be sent in batch by batch. You specify a batch size. The batch size is about 100. And so the 60,000 will be sent in batch by batch, in which case you will have 600 batches, right? 600 batches of 100 images each. The entire process is being done step by step, and the weights and biases are being normalized. Now, then you again shuffle all the data, then send it again batch by batch. So that entire process is called one epoch. And then you use the data again, but now you shuffle it. So the old batches are not the same as the new batches. Now it's like shuffling a deck of cards. You take the 60,000 images, shuffle them, and then send them batch by batch. Another set, send them batch by batch, and so on. So you can run for however many epochs there are that are required in order to maximize the accuracy. So at this stage, you have the blue line is just to indicate the training loss, which is going down, and the green line indicates the validation loss. You see why does the validation loss actually is even less than the training loss? Well, simply because the training data has been sent to this image augmentation, and so the training data is actually now far more diverse. Not to mention, validation is a smaller data set than the training data set. So already the training data set is, it's much broader. So actually we expect this. We expect the validation loss to be even less, and similarly validation accuracy to be even more. And you get about what, at this stage after 4 epochs, we get 87% accuracy on the validation. Okay, so so now that because now the model can be used to predict for new data set. You just need to feed in the data at the same 28 by 28 pixel format, and it will generate for you the probability of it being one of those 10 classes. Okay, so I think we will stop with that. So right now, if you have any questions, please now's the time to respond. If you have anything else, anything you want me to elaborate on. Yeah. Okay, could you please elaborate on convolution? Right. So this is actually what we had looked at. Let's go back. In the standard neural network, you just have a bunch of weights and biases connecting each layer to every other layer fully, in the sense that every value in one layer is multiplied by weights and biases. Multiplied by weights and biases are added to generate the values in the next layer, right? So you have three, in the input layer you have three values that are sent in, and you need to generate these 4. That means you will have 4 into 3 weights plus 4 biases, right? Now, if you are doing with, say, a picture with some 28 by 28 pixels, then you will have that the number of inputs will be 28 into 28, and then suppose the next hidden layer you want to generate will also have, say, suppose you want to say 1,000 neurons in the next layer, then you'll need 1,000 into 28 into 28 weights, and the number of weights simply goes way up. So instead of doing it like that, what you do is you use what is called a filter, which is a set of weights which is then applied across the entire image. It is not. It's not a set of, say, in that case, suppose you have a 28 by 28 image. You don't want to have a 1,000 into 28 into 28 weights connecting every pixel on the input layer to every pixel on the hidden layer. Instead, you just take a filter, which is a set of weights, which is then applied consistently across the entire image. So you apply it, say you just take this filter, make it sit there, 1 into 1 plus 0 into 1 plus 1 into 1 plus 0 into 0 plus 1 into 1 plus 0 into 1 plus 1 into 0 plus 0 into 0 plus 1 into 1. You just drag and drop it on that, and then keep moving along the image. So in this case, the number of parameters here is simply 5. And what you're doing is just use the same parameters across the entire image. And that this process is called convolution. Do a product sum on this. Apply it on the top left-hand corner of the image. Do a product sum, get out an output. Then keep moving it along the entire image and get out the output. And I showed you basically how that actually is able to identify certain features in an image, because based on the type of kernel that you have, it will be able to identify a particular feature of an image. How's that? Oh, what is a good rule of thumb on when you begin to flatten an image? This is, I mean, this I'm really not, I can't say, out of hand. It depends upon the data set that you have. Basically, you begin to flatten it out when when you are no longer able to treat it like an image. And look at let's see. You now go to full screen. Right. So now see, you have a bunch of. At this stage, you have a 13 by 13 image, right? If you go down in the next layer by doing another layer of convolution, you will get like 13 minus 5 plus an 8 by 8 image, which is not very easily interpreted as an image. So when you reach to that stage, when it becomes small enough, so small that a kind of a rectangular array of pixels is no longer you're no longer able to think of it as an image, then you flatten it out. That's all I can say. That is a good time to flatten it. Apart from that,
excellent. Thank you very much, everyone. And it provided a few questions. Please explain, Tiano. Oh, okay. There's one more question. Please explain, Tiano. That will be the last question for this session. Go ahead, please.
Yeah. So Tiano is like TensorFlow. It's a library in Python for handling tensor operations. So you can do the inner product, outer product, as well as certain optimization of gradient descent and certain other optimization techniques. Tiano. What I'm using I'm just using Keras as a high-level framework, and then the Tiano is being used as a backend. I personally, I have not used Tiano myself directly. I'm just using at this stage Tiano as a backend. It's like TensorFlow, very similar to TensorFlow in its architecture.
Okay, thank you very much, everyone, for coming and joining us today for this presentation, and thanks JK also taking this session with the students who are interested, with the learners who are interested. We will continue our topics, but next week I'll be here, but anyway, I will try to. We are going to talk about some topics on machine learning. Okay, so if you're interested, please join next week, same time. Thanks a lot, everyone. With this, it comes to an end for this session. Thanks a lot. Bye bye. Thanks, JK.